In this video, we're going to be studying the Hardy-Weinberg equation. In the previous video, we saw mechanisms of evolution, and remember we defined evolution or microevolution more specifically as being the change in allele frequencies over time. So for example, in this picture we can see we had 80% green genes, 20% brown genes. After a year, we now had 60% green genes and 40% brown genes, and it's because one of the conditions for Hardy-Weinberg equilibrium was not met, or maybe more, and then evolution occurred as a result of those conditions not being met. The first few slides will be review slides, just to frame the picture of Hardy-Weinberg equilibrium so we can understand the equation more effectively. Remember that when we study evolution, we need to understand the gene pool, which is essentially the collection of all the alleles in a population, and we want to see how those alleles, or the frequency of those alleles, or percentages of the alleles, change over time. Remember that organisms have a genotype, which is their genetic composition, what letters they have, and those letters determine what they look like on the outside, which is their phenotype. Because there's differences at the genotype level, you're going to see differences at the phenotype level as well, and that's why populations experience what's called variation. And since there's variation, evolution is able to occur, natural selection can act, and the populations can change over time as long as that variation is there. From the previous lesson, we know that there are many mechanisms of variation. We saw the ultimate source variation are the mutations, and then depending on how you reproduce, you could have meiosis and random combination of gametes. Another concept that we saw in the previous lesson was that we could calculate allele frequencies and genotypic frequencies if we had a picture of a population. So, for example, if I want to calculate the frequency of the dominant allele, we give that the letter P here. I could simply calculate the total number of individuals. There's 20 multiplied by 2 because there's 2 letters per individual. So it's 40 alleles in the population. Then I can go and count how many big A's I see, and then do 12 divided by 40 to give me 0.3 as the frequency of the dominant. I could also do the same thing for the frequency of the recessive. I give it the letter Q. That's what we're going to stick with for the remainder of this lesson. And same idea, total number of alleles, which is number of individuals times 2. Find how many little a's there are, do that division, and you get 0.7 as the frequency. It essentially means 30% of the genes are big A, or the alleles are big A, and 30% of the alleles are little a. You can then go and figure out the genotypic frequencies looking at this picture. You have 20 individuals. How many are big A, big A? Well, you can count. 1, 2, it looks like it's only 2 out of 20 that are big A, so 2 divided by 20, 0.1 are big A. And then you can do the same thing for the heterozygous individuals. We have 1, 2, 3, 4, 5, 6, 7, 8. 8 are big A, little a. 8 divided by 20, 0.4. And then you can do the same thing for little a, little a. You notice we have 10 out of 20 individuals that are little a, little a. So 10 out of 20 gives you 0.5. The reason we're using 20 here instead of 40 is because we're looking at the number of individuals themselves, not the allele specifically. And so that's how you can calculate allele frequencies and genotypic frequencies. And the main idea is that if P and Q stay the same from one generation to another, then the population is not evolving. The allelic frequencies did not change. But we can use an equation to actually figure that out. And that equation that we're going to use is the Hardy-Weinberg equation. So we had talked about the idea of the Hardy-Weinberg equilibrium, which essentially means that if the P and Q do not change, if the allelic frequencies are the same, then a population is in Hardy-Weinberg equilibrium. I abbreviate that as HWE. And if the population is in Hardy-Weinberg equilibrium, that's just another way of saying that the population is not evolving. In order for the population to be in Hardy-Weinberg equilibrium, you have to have all of these conditions met. No natural selection, no gene flow, no mutations, random mating has to be occurring, and the populations need to be large in order to avoid the effects of genetic drift. So if any of these conditions are not met, then it's possible that your gene allele frequencies will change, and as a result, you will not be in the Hardy-Weinberg equilibrium, and your population may be evolving. In other words, microevolution. So here we had an initial population, and we have the frequencies of the big A and little a calculated. They're 0.5 and 0.5 each. We can recalculate these frequencies in the next generation or later on. and we see that our big A is 0.25 now and our little a is 0.75. So since our frequencies are not the same, this is P over here, this is Q over here, this is P over here in generation 2, Q over here in generation 2. Since they changed, what that means is a population is not in Hardy-Weinberg equilibrium, that it is evolving. And it's probably due to one of the mechanisms that's not being met, or one of the conditions that's not being met in the previous slide and lesson that we discussed. And these are the mechanisms over here. So the Hardy-Weinberg equation. So if a population is in Hardy-Weinberg equilibrium, it means it's not evolving. So we can actually represent that mathematically using the Hardy-Weinberg equation over here. P squared plus 2pq plus q squared is equal to 1. So this equation represents a population that's not evolving. It's a model for a population that's not evolving. And so what you can do is you can figure out the p's and the q's for your population and compare it to a Hardy-Weinberg equation. If your p and q for an actual population matches the Hardy-Weinberg equation, then that means that your population is not evolving. If there are differences, if it doesn't match that equation, then your population is evolving. So again, the Hardy-Weinberg equation is a mathematical way to talk about the Hardy-Weinberg equilibrium. It's a mathematical equation that shows a population that's not evolving. If your population matches this equation, then what that means is your population is not evolving. If it doesn't, then it is evolving. So it's a mathematical way to tell if the population is evolving or not. And again, if the population is evolving, it's because of one of these conditions being violated. So let's go and explore the Hardy-Weinberg equation in a bit more detail. So again, here we have our mathematical model. P squared plus 2pq plus q squared is equal to 1. In the previous lesson, we had seen that p plus q is always going to be equal to 1. That's because the frequency of p and the frequency of q have to add up to 100%, which is 1 in this case. We write frequencies in decimal form, for example 0.7 and 0.3. That's why we say 1. But if you wrote it in percentage form, it would be 70% plus 30% is equal to 100%. So again, P represents the frequency of the dominant allele, and Q represents the frequency of the recessive allele. Now, those are allele frequencies. You can also figure out genotype frequencies or genotypic frequencies. It's the frequencies of the different genotypes in the population. And so the different parts of the equation actually represent different genotype frequencies. The P squared represents your frequency of homozygous dominant individuals. Remember, P represents your dominant allele. So if you multiply if you have AA, big A, that's your homozygous dominant, that's going to be P squared. So A is P, but AA is P squared. The Q squared is your frequency of homozygous dominant individuals. Remember that Q is your recessive allele. So that means that little a is going to be Q squared. And your 2pq is the frequency of the heterozygous individual. You have P and Q together. So P is big A, Q is little a. If you have big A and little a together, you have PQ. And we'll add a 2 there and we'll see why that is in just a bit. But those are all the different parts of the Hardy-Weinberg equilibrium. So if you have a population that's not evolving, and you figure out what P is and what Q is, you can then figure out the frequency of the homozygous dominant individuals by simply squaring your P. You can figure out the frequency of the homozygous recessive individuals by simply squaring the Q. And you can figure out the frequency of the heterozygous individuals by multiplying the P and the Q together and then multiplying that by 2 overall. And that's how you would use the Hardy-Weinberg equation to figure out your different frequencies if the population is not evolving. We can also use this equation to figure out if the population is in Hardy-Weinberg equilibrium, and we'll see that in just a bit. So let's just go explain why that is. Why is the Hardy-Weinberg equation written the way it is? So we have to go back and rethink our Punnett squares. Remember that Punnett squares, you have the gametes on the top and gametes on the side. Here we have sperm on the side here and ovum or ova plural on the top, and we'd have something like big A, little a, crossed with big A, little a. So that's our cross here. Now let's add in our frequencies in there. We know our frequencies for our alleles. We have big A is 0.7, so I put that here, 0.7. We have Q is 0.3, so I have 0.3 and 0.3. And then we do the fertilization event. So to get big A and big A, the chances of getting that together, remember multiplication rule, 0.7 times 0.7, and that gives you 0.49. But the main idea is that the chances of getting big A and big A, your dominant alleles in a heterozygous cross, is going to be P squared, P times P. What are your chances of getting P and P together? The chances of getting little a would be, chances of getting little a and little a together would be Q times Q. And that's why we get Q squared. For heterozygous individuals, what are the chances of getting P and Q? Well, it's P times Q. But don't forget, there's two ways for that to form. You can get Q from the sperm and P from the egg, and you get this result, or the other way around. You can get Q from the egg and P from the sperm, and you get this one. So that's why we have to multiply it by 2 for the heterozygous individuals. So the heterozygous individual frequency is not just PQ, but it's PQ plus our PQ or QP from the other way of forming it, and we get 2PQ. So this is the rationale behind the Hardy-Weinberg equation that was developed to model the Hardy-Weinberg equilibrium. If there's random mating happening, then by probability method, the frequency of homozygous dominant individuals has to be P squared. The frequency of homozygous recessive individuals has to be Q squared. And the frequency of the heterozygous individual has to be this and this together, which is 2PQ. So in reality, the Hardy-Weinberg equation is a probability equation. And so when you compare your population to that model, if the population resembles that model, then you can say that your population followed probability, there's nothing weird happening, so it's not evolving. If your population doesn't match that model, then it didn't really follow probability. Maybe there's something weird happening in your population, maybe there's natural selection, maybe there's non-random mating, maybe there's some kind of drift happening, maybe there's mutation and other mechanisms acting. So here we can see how to calculate, again, the allele frequencies and the genotypic frequencies. So this is a great example to start with. I'll do some more examples with you in a bit, but just take a look at the phenotypes here. So we have our 3 phenotypes that have been provided for our population, and we also have the genotypes that have been given, and we have the total number of individuals for each type of moth. So we have 320 of this one, 160 of this one over here, and then 20 of this one over here. And so if you want to calculate the genotype frequency from this data, what you would do is you would find the total number of moths by adding the number of moths of each type together, and that would be 500. And then if you want to figure out the frequency of the homozygous dominant, you'd simply do your 320 over here, divided by 500, and that's 0.64 for big A, big A. In other words, this would be your P squared. If you wanted to figure out the frequency of the heterozygous, you simply do the 160 divided by 500, because it's 160 heterozygous individuals, 500 individuals total. This would be 0.32. This would be your 2PQ here. And if you want to find your frequency of the homozygous recessive, simply do your 20 divided by 500, and you get your Q squared over here. Now what you'd find is when you add these all together, it would equal to 1, because these are all the individuals in your population. When you add the frequencies of all the individuals in your population, it should be equal to 100%. So if it's not equal to 1, then that means that you made an error somewhere, but it should be equal to 100%. You could also figure out the allele frequencies. You could do it simply by doing, we're going to do it the mathematical way right now, just looking at the picture actually. So we have how many alleles? We have 1,000 alleles. So if I want to figure out the frequency of big A, what I would do is I would have 1,000 alleles, find how many big A's I have. So over here I have 640 big A's, because there's 320 individuals that have big A, big A. And over here I have 160. So I have 640 big A's plus 160. That's 800 big A's total. That's a frequency of 0.8. Now, over here, for the little A's, I have 160 from the heterozygous, 40 from the little a individuals. That's 200. 200 divided by 1,000, that gives us 0.2. So our P is 0.8 and our Q is 0.2 in our population. And you can go back and verify to see that this matches. If you do P squared, we get 0.64. So far that matches the Hardy-Weinberg equation. Our P, if we P square it, we get 0.64, that matches the P squared. If we try the frequency of 2PQ of the heterozygous, let's see if that works out by using our formula. We'll do 2 times our P, 2 times 0.8 times 0.2, and we get 0.32. So that matches our Hardy-Weinberg equation. And we could do our Q squared, and let's see if it matches. So our Q squared would be our frequency of homozygous recessive individuals, 0.2 times 0.2, or just 0.2 squared, and we get 0.04. So these values here, when we plug them into our equations, they match what we figured out from the picture, which means that this population, I'll let you come up with the conclusion yourself. We'll see this in more detail. If it wasn't too clear now, after we do a few more sample problems, you'll understand it. So we're going to start off by doing problems where we assume a population is in Hardy-Weinberg equilibrium. So that's stated in the question. So in a certain population, you have 1,000 fruit flies, 640 have red eyes, while the remainder have sepia eyes. So we said that the sepia trait is recessive to red eyes. So assume Hardy-Weinberg equilibrium. How many individuals would you expect to be homozygous for eye color? So first of all, I'm going to write down this. We're assuming Hardy-Weinberg equilibrium. Hardy-Weinberg equilibrium has been assumed. Now, what do we want to figure out? We want to figure out the number of individuals that would be homozygous for red eye color. We know red eye color is going to be dominant based on the question that's told to us. So we know that red eyes need big R, big R. We want to figure out this frequency here. In other words, we want to figure out P squared. To figure out P squared, you're going to need to know what P is. So here's the tricky part. You're given some information. You're told that 640 individuals have red eyes. Now, sometimes students will be tempted to say, well, that's the number of individuals with red eyes, that's the homozygous dominant. Let's just divide that by 1,000 and we get 0.64. But don't forget, these red eye individuals could also be heterozygous individuals. So we can't figure out what P or P squared is from these 640 individuals because these could be big R, little r individuals or big R, big R. But here's what you do know. You have 1,000 individuals total. So how many individuals have the recessive trait? Well, that's simply 1,000 minus 640. And so you get 360. 360 individuals have the recessive characteristic. And you can actually figure out Q squared at this point. Remember that Q squared is the frequency of the homozygous recessive individuals. So we have 360 homozygous recessive individuals. I know that because it says here that the remainder have the recessive characteristic. And I can do divided by 1,000 total individuals. And that gives me 0.36. Now that I have Q squared, I can find Q. Q is going to be square root of Q squared, the opposite of squaring it, which is the square root of 0.36. Now, if you need a calculator to do this, I would recommend that you practice with your calculator that you're going to use during your test. It can't be your phone. You need to make sure you have a calculator you're comfortable with so you know how to do square root functions. So I would slow down and practice doing that. So now our Q is 0.6. Now remember, we want to find P squared. To find P squared, we need P. So remember that P plus Q is equal to 1. So to find P rather, all you need to do is 1 minus Q. And in this situation, P is going to be equal to 1 minus 0.6, and we get 0.4. So now that we have P, we can find P squared. P squared is going to be equal to 0.4 squared and you get 0.16. So this is the frequency of homozygous dominant individuals. Homozygous dominant individuals. Now the question though was not asking for the frequency. The question was actually asking how many individuals would you expect to be homozygous for the red eye color. So it's asking about how many individuals are you expecting. So for the number of individuals, I simply do the frequency, P squared, times the total number of individuals in the population, times 1,000. And that's going to be 0.16 times 1,000 and that would be 160 individuals that are big R, big R. And so this over here is my final answer. So to find the number of individuals, all you need to do is find the frequency of whatever number of individuals you're looking for, so it could be P squared or Q squared or 2PQ, and multiply by the total number of individuals in that population. So we have 160 big R individuals. We have 360 little r individuals, and you could probably find how many big R, little r's you have, right? If you add your 360 and your 160 together, that's 520. So that means the remainder must be the heterozygous individuals, which would be 480. Try to work through that to see if you can get to 480 for the heterozygous individuals. Even though the question's not asking for it, it's always good to try to work that out. So again, we did a question here where we assume the Hardy-Weinberg equilibrium. If the population is in Hardy-Weinberg equilibrium, you can find P and Q and figure out the frequencies of the other individuals by figuring out P squared, 2PQ, and Q squared where needed. So I could have changed this question to ask you for the frequency of heterozygous individuals instead. If I asked you for heterozygous individuals, you would have done 2PQ times total number of individuals. And let's see if that comes out to what we predicted. So times 1,000 is equal to, so P is 0.6 times Q is 0.4 times 2 times 1,000, and that gives us 480. So that's another way to figure out your number of heterozygous individuals, assuming you have Hardy-Weinberg equilibrium. Let's try this one out over here. Cystic fibrosis is a genetic disorder in homozygous recessives that causes death during teenage years. If 4 in 10,000 newborn babies have the disease, what are the expected frequencies of the 3 genotypes in newborns, assuming the population is at Hardy-Weinberg equilibrium? So we are asking you to find the frequencies of all the genotypes. We're asking you for P squared. That shouldn't be P2, that should be P squared. P squared. We are asking you for 2PQ. We are asking you for Q squared. Now, remember that the disease is recessive. So we told you here that these babies have the disease. What we told you over here is actually the frequency of little a, little a. You can figure that out. You know that Q squared is going to be equal to 4 over 10,000 individuals. that's going to be 0.0004. Now that you have q squared, you can find q by doing the square root of q squared, which is square root of 0.0004, and you get 0.02 as your q. Now that you have q, you can find p by doing 1 minus q, which is 1 minus 0.02, and you get 0.98. So let's just verify if that's correct. So 4 divided by 10,000, square root that number to get your q, 0.02, and do 1 minus that to get your p, we get 0.98. So now we can go and plug our numbers in and find the rest of the frequencies. So we can simply do our p squared, which is 0.98 squared, and that gives us the frequency of the homozygous dominant individuals, assuming a Hardy-Weinberg equilibrium occurring. So 0.98 squared, and you get 0.9604. And then we can do our 2pq, so 2 times 0.98 times 0.02, and we get, whoops, two times 0.98 times 0.02, 0.0392. You can verify your answer to see if they all add up to 1. So I'll do that number plus 0.9604 plus 0.0004, and I get 1. So when I add all these numbers up here, I get 1. If I had asked you for the number of individuals that are homozygous dominant, let's say that are big A, you would have simply done your frequency of big A, multiply it by your number of individuals in the population. So let's say 10,000. And same thing for heterozygous big A, you would have your frequency of big A, multiply by 10,000, and you already know the frequency or the number of individuals in 10,000 that would have it, which is 4. And again, we assume that the population was in Hardy-Weinberg equilibrium. So you should pause the video and try this one out yourself, and then compare answers afterwards. So the allele Y occurs with a frequency of 0.8 in clams. Give the frequency of the allele big Y and calculate the frequency of the 3 genotypes. Assume the population is at Hardy-Weinberg equilibrium. So we have the little y allele, which is our Q. Little y is our Q. So we were given Q of 0.8. Given that, you can find the big Y, which is P. So P is going to be equal to 1 minus Q, which is equal to 1 minus 0.8. And so that's going to be 0.2. Now that we have P and Q, what I like to do is to write down P and Q close to each other so I don't have to keep referring back to all my work I did. It's really easy to pick the wrong number on a test or a quiz or whatever you're doing. Now that I have those values, I can simply go in and find my frequencies for the things that were asked for. So I have my frequencies for the 3 genotypes, so P squared, 2pq, Q squared. So I'm going to say the answers and write them in. I'm not going to write out all the steps though, but you should be doing this. So for my P squared, I'm simply going to do 0.2 times 0.2, or 0.2 squared. So I get 0.04 frequency for the big Y. For my heterozygous, I do 2 times 0.8 times 0.2, I get 0.32 for big Y, little y. And for my homozygous recessive, I get 0.8 times 0.8, which is 0.64. And if you add those all up, you should get 1. And again, if I said there's 500 individuals, how many are homozygous dominant? You simply do your 0.04 times 500, and you would get 20 individuals that are homozygous dominant. So same idea for all these questions here, where you are assuming that Hardy-Weinberg equilibrium is occurring. Now, here are some more practice problems for you to attempt. Make sure you try these out. I'm not going to carry all of them through. I'm just going to write out the answers and maybe discuss the answers as I'm writing them out, but you should be carrying them through to make sure that you understand the concept and to make sure that you know how to show your work. So we have a population. There's 64 black cats and 36 white cats. Black fur is dominant to white fur. Assume the population is in Hardy-Weinberg equilibrium. Explain which phenotype you would want to use to calculate allele frequencies and why you would not want to use the other. Calculate P and Q, calculate genotype frequencies. Based on your genotype frequencies, calculate the number of black cats that are homozygous, calculate the number of black cats that are, I should have said heterozygous over here. So let's change that to heterozygous. And I'll go back and change this before I upload the video. And actually, I think I want to walk you through this one. You could try it out, but pause the video and then come back and see it after. So which phenotype would you want to use to calculate the allele frequencies? So remember that black cats are dominant to white cats. That's what we said over here. The black fur is dominant to white fur. So if I tried to figure out my P by using the black cats, I would be thrown off because remember, black cats could actually have more than one possibility in there. Black cats actually make up the P squared plus 2PQ part of the equation. There's too much going on there. You want to choose phenotypes where there's only really one letter that you're dealing with. And that would be your white cats. The white cats make up the Q squared part of your equation. Now, that's not, 36 is not directly Q squared. You need to actually do your divisions to figure it out, but usually when you want to figure out your P and your Q value, try to choose one of the homozygous individuals if you can. Typically the recessive individual is a better one to choose because you know for sure it's just Q, and that's it. If you choose the dominant individuals, there might be some heterozygous in there and you're not really doing the right calculation to figure that out. So what I would do in this case to calculate, I would start calculating my Q first. So let's call this question A. We just explained it. We'd want to use the white cats because we know they're Q squared solely, whereas the black cats, they're P squared plus 2PQ, and there's too much going on. You couldn't really isolate the variable with the information that's given there. So what we're going to do is we're going to figure out what Q is first and then go and find our P. So for the Q value, I need to find Q squared first actually, because with the information I have here, I can find what Q squared is. So let's find Q squared. So let's do B over here. Q squared is going to be equal to 36 white cats over the total number of cats in the population, which is 100. So Q squared is going to be 0.36. Now that we have Q squared, we can find Q by doing the square root of 0.36, and we get 0.6. Now that we have Q, we can find P. P is equal to 1 minus 0.6, and we get 0.4. Now that we have our P and our Q, we can go and do question C, which is calculate the genotype frequencies. So our genotype frequencies are going to be our P squared, our 2PQs, and our Q squareds. So our P squared is going to be our 0.4 squared. 0.4 times 0.4, which should be 0.16. For our, let's call this big B, homozygous dominant. Our heterozygous individuals are going to be 2 times 0.4 times 0.6. That's 0.48. For big B, little b. And our Q squared, that's going to be 0.6 squared, which is 0.36. So we already figured that out in the previous question, but that's our Q squared is going to be little b. So now, using that information, we can figure out question D and question E. We want to figure out how many black cats are homozygous, how many black cats are heterozygous. So for D, we take our frequency of homozygous individuals, 0.16, multiply it by the total number of individuals in the population, not just number of black cats, total individuals in the population, because this is based on total number of individuals, times 100, and we get 16. Now there's two ways to do E. You could simply do 64 minus 16, because that would be the remainder of your black cats. Or you could do your actual frequency calculation. So you can do heterozygous 0.48 multiplied by 100, and you get 48. If you add these numbers together, you should get 16 plus 48, 64 black cats total. So now out of the 64, you know which ones are homozygous dominant and which ones are heterozygous. Here we have a variety of practice problems related to the Hardy-Weinberg equilibrium, assuming Hardy-Weinberg equilibrium is occurring. This is on your worksheet, but I've also included it in the PowerPoint here, so you can try these out before moving on to the next part of the video, or you could try them all at the end. I highly recommend, though, that you do at least try one or two before moving on to the next part of the video. Here are some more practice problems where you assume Hardy-Weinberg equilibrium. Another type of question that you might see with the Hardy-Weinberg equilibrium is one where you have to check if a population is in Hardy-Weinberg equilibrium. In the previous questions, you were told to assume that it was. And so we could simply do p squared, q squared, very simple calculations to figure out what our p squared, p and q's were. Now, sometimes you might be given some information about a population. You might be given the exact genotype numbers for each type of individual, and you'll have to figure out if that population is in Hardy-Weinberg equilibrium or not. So when you don't know if it is, you have to calculate the p's and q's in a bit of a different way. So first we're going to figure out this population here. We're going to figure out if it's in Hardy-Weinberg equilibrium by realizing that these are observed values. We went into population, we made observations, and these are observed values. And the idea is that we want to figure out our p and our q for the observed values, and then use the p squared, 2pq, q squared to see if the observed values would match what values we should get using that equation. If they match, then the population is in Hardy-Weinberg. If they don't match, then the population is not in Hardy-Weinberg. So let's try that out. So I can't simply do 16 divided by all my individuals because I don't know if the population is in Hardy-Weinberg. I can't do that right now. So what I have to do to figure out my q's is I can figure out how many total a's there are, little a's. Well, there's 32 from the 16 little a individuals, plus 48 from the big A little a individuals. And so that's going to be 32 plus 48, a total of 80 little a alleles. And so I can now find my q by simply doing my total number of alleles, 80, or total number of little a alleles, over the total number of alleles in the population. So there's 36 plus 48 plus 16 36 plus 48 plus 16. Multiply that by 2 because there's 2 alleles per individual. That's 200 over here. And so my frequency of Q is going to be my 80 divided by my 200. And that's my 0.4. So based on that, now I can do my P. P is going to be equal to 1 minus 0.4. And that should be 0.6. You could have instead figured out the frequency of the dominant allele by doing 72 from the big A plus 48 from the big A little a. That would have given you 120 big A's. And then you could have done your P is equal to 120 over 200 for the number of alleles total. And you would have obtained 0.6 as well. So that, and then you could have found your Q from your P there. But now we're going to go and find what our expected values should be using the Hardy-Weinberg equation. So expected values, we'll call them E for expected. P squared is going to be 0.6 times 0.6. That's 0.36. So in a population of 100 individuals, which is what we have here, we would have 36 big A. So let's go write that right underneath to make sure that we can compare them directly. Our 2PQ would be 0.6 times 0.4 times 2, 0.48. So in 100 individuals, that would be 48 big A little a's. So let's go write our expected over here, 48 big A little a's. And our Q squared would be 0.4 times 0.4, 0.16. That would mean 16 individuals in 100 that are little a. And so because our observed match our expected from the Hardy-Weinberg equation, we can say that the population is in Hardy-Weinberg equilibrium. Therefore, it's not evolving. Now, some students might have said, well, sir, if it's in Hardy-Weinberg equilibrium, why didn't you just go and do your Q squared like you normally would? Well, remember, we didn't know that it was in Hardy-Weinberg equilibrium. We had to do this test to figure it out first. If we simply assumed it was and we did our Q squared the way we did in the previous questions, we would have made a few mistakes. So if you didn't quite follow all the steps here, you should rewind the video and retry this for yourself to make sure you understand what's going on. There's a practice problem given at this link over here. It's a little tutorial that you can use to practice doing these type of questions. If you don't know that the population is in Hardy-Weinberg equilibrium, to calculate P, you need to find all of your big A's, divide by the total number of alleles, like we did in the picture. And to calculate Q, same thing. You need to find all your little a's divided by the total number of alleles. You can't simply do your Q, your number of little a individuals, over your total population, because we don't know if it's in Hardy-Weinberg equilibrium or not. So let's do another sample problem here together. You can try it yourself first, pause the video, and then go back and attempt it yourself. And then come back and check my answer. So here we have some flies that are bred in the lab, and we have 3 different eye colors. We have the regular eye color, we have the red eye color, and we have the pink eye color. And so what we want to do is we want to write down our observed values first based on what's given in the question. So we have, how many have regular color, normal eye color? So 90 have normal eye color, so 90 would be our homozygous dominant based on the question. So that's why it's important to really understand the genetics component that we did earlier. The pink eyes would be 45 have pink eyes, so 45 are heterozygous. We have a case of perhaps incomplete dominance here. And then 15 flies have red eyes, which is our little r, little r. And we want to check if the population is in Hardy-Weinberg equilibrium. In the previous questions, we knew they were in Hardy-Weinberg equilibrium, but in these questions, we don't know if they are, so we have to try to see if our observed match our expected. So let's try to find our Q's first. So for Q, I have 30 little r's from the 15 little r individuals, plus 45 from the heterozygous individual. So 30 plus 45, 75 total. So this might work for my Q. 75 total little r's. So to actually find the Q value, I need to do my 75 divided by my total number of alleles. I have 150 flies, so that's times 2, 300 alleles. So 75 divided by 300, 0.25 for my Q. Now I can find the P by doing 1 minus Q. And that's going to be equal to 0.75. So now I can go and figure out if my expected would match my observed. So if the population were in Hardy-Weinberg equilibrium, I would expect P squared. I would expect that frequency for my homozygous dominant individuals. So 0.75 times 0.75, 0.563. I'll keep 3 decimal places, 0.563. And out of 150 individuals, so times 150, that would mean that I have about 84 individuals that are big R, big R. 84 big R, big R. Let's go take a look at the 2PQ. So for 2PQ, I have 2 times 0.75 times 0.25. 0.375 is my frequency of heterozygous individuals. If I have 150 individuals, I have 100 times 150. I should have about 56 individuals that are big R, little r. And now I can do my R squared, my Q squared, sorry, which is going to be 0.25 squared, 0.0625. In 150 individuals, that's going to be times 150. About 9 individuals that are little r, little r. So because my expected and observed do not match, so observed do not match expected, my population that I observed is not in Hardy-Weinberg equilibrium. Therefore, the population is, or may be, evolving. This question is a similar question to the one that we previously did. The only thing is you have to do that work that we did for each of these populations. So you have 4 different populations. You want to see which ones are in Hardy-Weinberg equilibrium for a particular gene A. Now, just a quick little clarification or oversimplification that I was making. When we compare the observed and the expected, in reality, there can be some slight differences between them, and the population can still be in Hardy-Weinberg equilibrium. You might have a difference of 1 or 2. How do you know if those differences are acceptable to still be considered Hardy-Weinberg? How do you know if it's really just due to some random chance and not some evolution? Well, you'd have to do a statistical test. That statistical test would be something called a chi-square test. And so if you did a chi-square test, that test would tell you, yes, your variation that you see is due to random chance. It's not due to natural selection or some other mechanism of evolution. But in grade 11, we're not really going to focus on those. We're not going to see those statistical tests, but just understand that there are statistical tests in order to see if those differences are called significant differences, statistically significant differences. But in grade 11, we'll assume that any difference that we see is going to be statistically significant, even though in reality it's not the case. So before doing this video, before completing this video, you should actually pause the video and try this yourself. See if you get the right answer. I'm not going to carry the whole thing out. I'm just going to let you know what the answer is so you can go back and check if it matches. Once you're done, you should see that populations 1, 2, 2, and 3 are in Hardy-Weinberg, but the population 4 is not in Hardy-Weinberg, so your best answer would not be 2 and 4. It would not be just 1 and 3. It would not be all of them, and it would not be 4 only. It would be 1, 2, and 3 only, because 4 is not in there. So try them all out just to see if that's actually correct, and if you reach that conclusion, then that means you've done these problems correctly. So now you should be at a point where you can solve problems for Hardy-Weinberg equilibrium. So if I gave you this picture over here, would you be able to figure out if the population is in Hardy-Weinberg equilibrium? So if I didn't tell you to assume it was, can you figure out what the little a frequency is, what the big A frequency is, and then see if your expected match your observed? And so you should review the PowerPoint. You should complete the practice problems on the PowerPoint and the worksheets. There's a little reading that you can do in the textbook, and there's some great practice problems that you can watch at this link here. And there's an excellent lab that you can try out. It's a virtual lab over here. Don't forget, you do have a gizmos to complete for the Hardy-Weinberg equilibrium. So after you complete that gizmos, you might understand the concept in more detail as well.